So, section 4.3 is about analysis of algorithms. And essentially, what we're trying to do here is to approximate how long a program or an algorithm has to run before it is completes its task. Okay? So, here's an interesting little table to show you that how the efficiency of an algorithm can have a tremendous impact on the amount of time it needs to complete. So this table here, let's see what we have here. The number of steps to termination for an input of size n. So these are the inputs, right? 3, 6, 9, 12, 50, 100, et cetera, et cetera. And if we know that it and if we assume that it takes 10 to the negative 6 seconds to make one calculation, right? Then it would, if it terminates in one step, right? It would just take 10 to the negative 6 seconds to complete the program. But if it were to take, say, n, right, where n is 3, notice that it would be 3 times 10 to the negative 6 seconds. In other words, it takes 3 times as long. If we knew it took, say, 2 to the n, well, 2 to the n in this case, where 3 is just 8, so it's 8 times as long. Now, for small inputs, right, it's not a big deal how fast the program runs, but as the number of input size, if it increases to, say, 50, look at this, if we had a program that ran so that it would take 2 to the n steps to complete, it would take 36 years to finish running the program. So it's very important to know how our algorithms are structured so that we can avoid this exponential nightmare here of 2 to the n, right? Okay, so there are 3 types of things that we're interested in when we look at algorithms: the best case time, the worst case time, and the average case time. So we're going to look at ways of calculating this number based upon looking at our algorithms. So here's an example in this one where we look at this algorithm for 2.12, right? That finds the largest value of a finite sequence, right? So if you have a finite sequence, we know that it takes this n minus 1 steps to complete. It compares n minus 1 things. So it's always executed in n minus 1 times, okay? Well, usually this is interesting, a very good sentence here we're talking about here. So usually we're not interested in, the exact time. We just want to know how the time grows as n increases. So, for example, suppose that the worst case time for an algorithm is the t of n. So if the input size is n, the number of times it has to iterate is 60 times n squared, this polynomial. Then we have this, let's look at this table down here. For input size n, for large n, this term right here, this 60 times n squared, is approximately equal to t sub n. So let's take a look at that. So here you see n is equal to 10. Well, the exact answer, if that in fact is the t sub n, would be 6,051. But notice that that's actually very close to just 6,000. So what we're really interested in is trying to figure out what the sort of largest term in this finite sum is, in a sense. So, all right. So let's look at that. So here's the definition, and here's how we do it. This is kind of a long definition, but essentially it's what has to happen. Okay, so here's the deal. So if f and g are these functions with the domain the integers, we write that f of n is big O of g of x if this inequality is satisfied. Essentially, that well, you can read it as well as I can, but that this function g of x actually is bigger than fn of x times some constant times the absolute value of gn of x, right? For all but a finite number of positive integers, okay? So that means like eventually a good way to think of this is that some constant times g, the absolute value of g of n is actually larger than fn. So you've got this definition, and then, okay. So that's the way we write this big O of g, right? So we write fn is this omega of gn of x if, in fact, f of the function that we are interested in is actually larger than or equal to some constant times gn of x, okay? For all but a finite number of integers. We'll do some examples. So we write that fn of x is actually equal to theta, we say, of n of x, and we say f is of order g of x, or f is theta of g of x if f is equal to O of g of x and f is equal to omega of g of x. In other words, this idea of being of order g of x is the idea that it grows very similarly to this function g. So here's some examples, I guess. Let's look at some examples. Here we go. So here's an example. Since this polynomial that we looked at first, right, we see that it's actually less than or equal to 66 times n squared for all n greater than or equal to 1, right, because we just sort of made this up. Then we would, if we take C1 equal to 66 in that definition, we can see that this 60 times n squared plus 5n plus 1 is actually big O of n squared. It's approximately grows like n squared, we would say. Okay? And since, in fact, this 60n squared plus 5n plus 1 is actually greater than or equal to 60n squared for all n greater than or equal to 1, if we take C2 equal to 60 in the definition, we can see that, in fact, this function is actually omega of this n squared. Okay, well, since we have that it's both big O of n squared and omega of n squared, we conclude by our definition that, in fact, this function that we have calculated is basically or grows like n squared. And that's the idea. We want to know how our algorithm that we might be interested in is growing. Okay. Okay, so here's a little theorem you can read. You can imagine this is correct. More than imagine, you can see that a sort of a generalization of this example would give us this theorem that if you have a polynomial which has degree k, it grows like n to the k. Okay, and here's a proof of it. I don't want to go through it. I'd highly recommend reading it though. But here's what you want to look at. Okay. Here's some functions that will arise as a result of our investigations, and you can see that, for example, if you have these functions, here's how these functions look. So we might say, oh, y squared. Okay, the one function we could see that more or less grows like n squared, right? Or if we found out that a function grew like 2 to the n. This obviously the coordinates have been shrunken down here. This is a line, so this must be logarithmic graph or something. But so the big one here that we want to avoid when making algorithms is this y equals 2 to the n. Okay, in a nutshell, that's what's sort of going on here. Let me look at another. Read through these things. Here they're doing some examples. They're showing us that, if I look at this here, there's a good, let's look at this. If we replace each integer 1 through n by n in the sum, right? Here we go, 1, 2, 3, out to n, right? Then watch what happens. Well, that means that this function is big O, right, of what? Like n squared. See, that's what they're saying here. Right, it follows that when you sum up these things at big O of n. And then to obtain a lower bound, okay, so let's take a look at a lower bound. We might imitate the preceding argument and replace the integers, 1 through n by 1, right? in the sum. So if we do that, that makes sense. That's n, right, for all n. So in other words, on this one, you're showing that it's smaller than something, and over here we're showing it's bigger than something else. So in this case, we would conclude that this thing is omega of n. But notice that since those two are not equal, we can't really conclude that they grow that by this argument that they grow as n squared. Okay, so sometimes you have to be a little bit sharper, we would say. We have to get a little bit better approximation. So the way you do that is you essentially do what they're saying. You take the first half of the terms to obtain this following thing. All right, and then you get this this thing is greater than or equal to n squared over 4. You can look at that, and that's how we can conclude that in fact the sum 1 through n is it grows like n squared. Okay, so et cetera, and that's the type of calculation that you will need to do at times when dealing with algorithms. Okay, so here's some definition that we kind of need to look at here. It says, I'll just read it. So if an algorithm requires t of n units of time to terminate in the best case for an input of size n, and if t sub n grows like g of n, we say that the best case time required by the algorithm is of order at most g of n. Okay, so same thing here for the worst case, right? If we know the worst case is like g of n, then we say, that's when we say that the order of most that for g of x, et cetera, okay? So notice here we're trying to get an upper bound on how much time it takes, right? So if you have this, we would say that the average case time required by the algorithm is of order at most g of n. And it's really important to be able to approximate this, because this tells you how long you can anticipate the program would take to terminate, okay? And similarly, if we replace O by omega, then we can, and at most by at least in this definition, you get an analogous relationship between the runtime of the algorithm that you're looking at and how it grows, okay? So let's take a look here. Here's our example. So we would say, suppose that an algorithm is known to take this 60n squared plus 5n plus 1 units of time to terminate, right? Well, in the worst case, the input of terminate in the worst case of the input of size n. Okay, what does that mean? Well, we showed this one example, that this function is of order n squared. So thus, the worst case time required by the algorithm is order of n squared. May not be exactly n squared, but some constant, right, times n squared. That's how it grows. That's how it gets larger. Another example here. Okay, here we go. Here's a good type of question. Find the theta notation in terms of n for the number of times the statement x equals x plus 1 is executed. And here's our algorithm, right? Okay. So what does it do for I equals 1 to n? And then for j equals 1 to I, you calculate, okay? So you can see that when, and sort of looking down here, you can see that when I is 1, it calculates once. When I is 2, it calculates 2 more times. I is 3. So what we see is that this thing, the number of times that the statement x plus 1 is executed is 1 plus 2 plus 3 all the way out to n, and that's of order n squared, right? Thus, the theta notation for the number of times the statement is executed is order of n squared. Okay, now this is a really good example to look at because it will give you sort of an idea of the types of calculations that one needs to do when dealing with this. Okay, so let's do the same thing, but now here's a different algorithm. So how does this algorithm work, right? Okay, so here we go. So I is n, right? And then while I is greater than or equal to 1, right, what we do is we execute x is x plus 1. And then I is, well, you basically divide I by 2, right? And then you take the floor function of it. Okay, let's see what happens. So we want to try to calculate how long this will run, right? So here's the first thing. So when you're working on a problem like this, you have to actually go through it and think about it, right? So, but this is a really good trick they're showing us here. First, we examine a specific case because of the floor function. Now think about this. The computations are simplified if n is a power of 2. That makes a lot of sense because when it's a power of 2, then each time you do this, I is equal to I divided by 2, you're just removing the exponent, okay? So let's consider, for example, the case when n is equal to 8. All right, so when n's 8, at line 1, I is set to 8, and at line 2. So you really have to think about this stuff when you're doing this. And the condition I is greater than 1 is true. At line 3, we execute the statement, right? You execute the statement, right? And then what happens? At this line, it gets turned into a 4, right? And then I is reset to 4. You go back up here, right? And then we return to line 2. And that's true, and you go around. But eventually what you see is that the statement, eventually it becomes, 0, right? And then what happens, once it's reset to 0, we know we return to line 2, and the statement at line 2, the condition I is greater than 1 is false. So the statement x equals x plus 1 was how many times? It was executed 4 times, okay? So we can see by going through this thought experiment that it was executed 4 times. And then now suppose n is 16. Well, then you start to realize 16 then turns into 8, okay? So, right, after you cut it in half, and then 8, that's the previous case. So you can then conclude that a pattern is emerging, right? You can see that it for a total of 5 times, right? See that? 4, then 5 times. One more time each. So similarly for 32, the statement x equals x plus 1 is executed 6 times, right? So you have to see this pattern emerging, and each time the initial value of n is doubled, the statement x equals x plus 1 is executed one more time. More precisely, if n is equal to 2 to the k, the statement x equals x plus 1 is executed k plus 1 times, okay? So we see that. Now, here's the punchline, kind of. Since k is an exponent of 2, for 2, k is actually equal to the logarithm of n. Thus, that's where we get our statement. Thus, if n is equal to the k, the statement x equals x plus 1 is executed the 1 plus the logarithm of n times. Okay, however, we need to know this formula is correct for arbitrary n. So here's where there's a really wonderful trick that you'll need to employ when doing some calculations. So now we take, okay, so if n is an arbitrary positive integer, not necessarily a power of 2, that means it lies between 2 powers of 2. Thus, for some k, we would know that 2 to the k minus 1 is less than or equal to n is less than 2 to the k. Now, so we use induction on k. We're going to prove this formula by induction on k to show that in this case, the statement x x equals x plus 1 is executed k times. See, if k is 1, we know that 1 equals 2 to the 1 minus 1 is less than or equal to n, right? Is less than 2 to the 1 equals 2. So therefore, n is 1, right? In this case, the statement x plus 1 is executed one time. Thus, the basic step is proven. Okay. Now, so to do induction, now suppose that we have, if n satisfies this, right? Right now that k is greater than 1, then you do this. The statement x equals x plus 1 is executed k times, right? We want to show that. So we must show that if n satisfies this, the statement x equals x plus 1 is executed k plus 1 times. Okay, how do we do that? Well, let's see. Suppose n satisfies this inequality. So at line 1 of the algorithm, I is set to n. At line 2, the condition I is greater than or equal to 1 is true. At line 3, we execute the statement x equals x plus 1 the first time. At line 4, I is reset to the floor of n divided by 2, and we return to line 2. Notice that when you do that, 2 to the k minus 1 is less than or equal n over 2, right? N divided by 2 is less than or equal to 2 to the k. Well, that's because, 2 to the n minus 1 is an integer, right? So we must also have that this is true. But now we use the inductive assumption. So by induction, the statement x equals x plus 1 is executed k more times, okay, for a total of k plus 1 times. The inductive step is complete. Therefore, if n satisfies this condition up here, the statement x equals x plus 1 is executed k times, and that's what we wanted to prove. Now, suppose that n satisfies that. Taking logarithms to the base 2, we have k minus 1 is less than or equal to logarithm of n is less than k. Okay, so well, wrapping it all together, we can see that this algorithm, you can read this, actually executes at order logarithm of n. Okay? Those are the type of calculations that are done. I guess as one sort of, let's see, last thing that I would like you to read, make sure you read through this and look at, this is something that is very deep subject. So look at these comparisons. Here's our growth functions. These are standard growth functions: constant, log n, n log n, n squared, n cubed, n to the k, c to the n factorial. Okay. So look at these, and this is where there are certain terms that are defined in complexity theory that talk about different types of algorithms and their, whether they're, feasible or tangible or intractable, right? Or there's a concept of NP complete, right? And I don't want to get too into that because it's a little esoteric, but it's also very important. So read through the rest of this section, and I recommend that do a Google search on NP complete, and there's probably 100 videos detailing the importance of that. So anyway, that's my little introduction to 4.3, and there's some assignments in there where we'll carry out these types of calculations. So okay, hope this helps. Thank you very much.